Hello everyone and a very warm welcome to all of you in this competitive math masterclass. What we will do in this session today is problems from competitive math. Competitive math is math that is more advanced compared to school level math. It has questions that might seem more difficult from what you typically do in school, but with the right strategies, with the right techniques, all of you can easily solve the problems we will do today. And these problems come on various kinds of math contests. You might have heard of some of them. There's Math Kangaroo, there is MOEMS, MOEMS, there is AMC 8, there's Math Counts, and there are many more math competitions like this. And some of you might already have participated in such competitions. Some of you might be wanting to. In this session, I will help you understand how to solve problems that come on such math contests. All right, so let's begin. What we will do first is a set of problems from Math Kangaroo. So this is the first section, section 1, and what I've done here is I've taken the past couple of years, 2 or 3 years of problems from grade 3 and 4 and some problems from grades 5 and 6. I believe that all of you here are from grades 3 to 5. So these questions that you see that we will discuss now are aimed at your level. So that is what we are going to get into now. As I said in the beginning, I will be showing you questions, I will be sharing problem solving strategies and asking you to solve some problems on your own, and then I want you to share your answers in the chat window. All right, so let's see. The first question here says Alice has these 4 jigsaw pieces. So you can see these 4 jigsaw pieces, and it is asking you which 2 pieces can she put together to make a square. So which 2 pieces can be put together to make a square. So what you have to do here is mentally visualize which 2 pieces you could move in a way that they could be fit together to form a square. So how do you do this mentally? Well, you can start with figure number 1, and you can see that there is an outline of a square that you see, but there are certain parts or certain regions that are missing, and you can try to see if any other piece could potentially fit into this missing region here. And the way to do that simply is to just count the number of missing squares. So you have 3 missing squares here, you have 2 missing squares here, and you have 2 missing squares here. So 3, 2 and 2. And if you now look at figure number 4, it has 3 squares like this, 2 squares here and 2 squares here. So if you were to pick this figure and place it over here, it would fit in exactly into this missing region, and therefore 1 and 4 will combine to make a square, and I can see many of you have correctly answered. So that's how you do it. But if you look at, let's say 2 and 3, would they fit? So you need 3 here, 1 here and 2 here, but you have 4 here, 2 here and 2 here. So this piece won't go into this piece. So these 2 won't fit together, but 1 and 4 will fit together. So that's the answer to this question. It is an actual question from last year's Kangaroo Math. So great job to all of you who were able to successfully solve it. Now here's our next question. It says Maria switches the lights on and off according to the given plan. So light 1 shows, these bars show the minutes during which the light was on or off. So light 1 was on, for example, between minutes 1 and 5, then from minutes 6 to 9 and so on. Light 2 was on according to these orange bars, light 3 was on according to these blue bars, and it's asking you for how many minutes in total are there exactly 2 lights on at the same time, exactly 2 lights on at the same time. For how many minutes are exactly 2 lights on? So I can see Prakash Selvaraj, I think, has the first correct answer. The correct answer here is 8. So I want you to follow me carefully as I explain how you can do this. So you have to look at every window of time and basically look at if there are 2 bars that exist in that window or not. So if you look at this first window here, minutes 0 to 1, or the first minute, you will see that only light 3 is on. But if you look at this window here, you can see that light 1 and light 3 are on, and then in this window again you have 2 lights on, in this window you have 2 lights on, in this window you have 2 lights on, and so on. So, but then in this window you have 3 lights on, so you don't take this window, then you take this window and this and this. So, let us count all the windows where there are windows of time where there are 2 lights on. So, you have 1, 2, 3, 4, 5, 6, 7 and 8. So, there are 8 minutes during this time when exactly 2 lights are on. So, the answer is 8 minutes. All right, great job. I can see a lot of correct answers. Yes, all right. Okay, let's keep going. Here is the next one. Once again, an actual question from a Kangaroo Math contest. You have this arrangement of coins that you see, and one of the 5 coins A, B, C, D or E shall be placed in an empty square so that there are exactly 2 coins in each row and in each column. So, you want exactly 2 coins in each row and each column, and you have to move one of the 5 coins to do that. So, which coin will you move and where will you move it to? Which coin will you move and where will you move it to? I can see a lot of answers saying B. All right, let's see if B is the correct answer. So, if you look at this first column here, it has 3 coins, and if you look at this row here, that also has 3 coins, but you want 2 coins per row, you want 2 coins per column, and therefore you need to take out this coin C. Okay, if you take out B, where will you put B on? I don't see any answers telling me where to move the coin. So, you have to look at every row and every column. So, in every row, in every column, let's count the number of coins. So, column 1, 3 coins in column 1, then 1, 2, 2 and 2. So, this column is problematic because there are 3 coins in this column and this column has only 1 coin. And now, let's look at the coins in every row. So, 2, 2, 2, 1 and 3. So, this column has 3 coins and this row has 3 coins. So, if I take out this coin and move it here like this and remove this coin from here, now in this column I get, instead of 3 I get 2 coins. In this row, because this coin has moved out, I get 2 coins here, and because C has now moved to this place, I have 2 coins here and 2 coins here. So, that is how you have to do it. So, the answer is saying coin B. That answer was incorrect. The actual answer here is coin C. You have to move coin C from this position here to this position here. All right, that's the answer in this case. Now, this one is a very different kind of problem. There's a laser beam that hits a mirror, and once it hits a mirror, it changes its direction. Like if you notice this diagram here, which tells you how the rays and the mirrors are behaving. So, if you go like this, the mirror reflects the ray like this and so on. And now, this is the problem image, and it's asking you, each mirror has mirrored sides on both sides. At which letter does the laser beam end? So, where will this laser beam end up once it is through with all the reflections in this image? Where will it exit, or where will it end? Which letter will it get to once it has gone through all the reflections? Okay, I can see a mixed set of answers. So, I am going to do this one for you, and we are going to do the reflections step by step. So, the ray enters the box here. So, it should first get reflected here. Then this mirror should reflect the ray over here. Then this mirror should reflect the ray over here. Then this one should bring it here. And then this mirror should reflect it here. And then this mirror would reflect the ray back here. And then this mirror would reflect it down like this. So, this is how the reflections will happen, and the ray will exit the box here at point B. So, B is the answer in this case. I saw a lot of D's as answers, but D is not correct. The actual correct answer is B, and I hope you understood the logic here. Okay, here's the next one, again a Kangaroo Math question from last year. You have these 5 pieces that you see at the bottom of the screen, A, B, C, D, E, and using the pieces A, B, C, D and E, you have to, or you can fill this shape completely. So, which of the pieces among these 5 will end up lying on the dot? which piece among these 5 pieces will lie on the dot. I don't see too many correct answers so far. I see a lot of D's, some C's. So we are going to do this step by step systematically. So please observe how I'm going to do this. Please follow me carefully. And the thing to do here is to carefully visualize in your mind which piece will go where. So I could start with this piece here, because this one immediately is evident that it will fit at this corner here like this. So this piece comes over here like this. Okay, so this is piece C, and then I could take this piece B and put it over here like this, and then I have this empty region which I could fill with piece labeled A like this. All right, so piece A goes here, and piece B has come over here, and piece C has come over here, and now I'm left with pieces D and E. It's immediately clear that piece D should come over to this left here, because it has this vertical edge at the left, so that should be piece D. And now I'm just left with this empty region in the middle, which can be filled by piece E. So it's clear now that piece E is what will come over the dot. It will lie on the dot. So E is the answer in this case. So this is how you have to solve problems like this. You have to mentally rearrange these pieces or such pieces in your mind to see how they are fitting together to form the original picture. All right, let's keep going. Now this one is very interesting. So you have 4 cars labeled 1, 2, 3 and 4, and the arrows show the directions the cars will move. Which cars will crash into each other? So you have to imagine that right now these 4 cars are where they are positioned, and then they all start moving in the directions shown to you at the same time. Which 2 cars will crash into each other? That is the question here. Which 2 cars will crash into each other? Okay, so how do you think about this? Because it seems like car number 1 and car number 3 could be headed on a collision course, and similarly car number 4 and car number 2 could be headed on a collision course, and then 3 and 2 are headed right into each other. So which 2 cars will crash here? Well, let's look at cars 1 and 2 and car 1 and 3. Car 3 is going like this, car 1 is going like this, and we will first investigate if these 2 cars will crash into each other or not. Well, if you just look at the distance these 2 would have to travel to crash into each other, the only point they could meet is this point here, and car 1 would have to travel this distance and car 3 would have to travel this distance if they had to crash over here. But it's visually obvious that this distance is larger than this distance. So this distance is longer than this distance, and therefore by the time car 1 reaches here, car 3 would have crossed that point. So that's the key idea here. By the time car 1 would have reached this point, car 3 would already have crossed this point. So car 3 won't crash into car 1, it will kind of go over like this, go ahead like this. Similarly, cars 2 and 4 could potentially crash at this point, but by the time car 2 reaches over here, car 4 would already have crossed this point. So car 1 will not reach this point, car 3 will cross, and car 4 would already have crossed this point by the time car 2 reaches over here. So therefore, cars 3 and 2 are the ones that will ultimately end up colliding with each other. So 2 and 3 is the answer. So those of you who got it right, congratulations. You actually solved a fairly tough question, although it might seem easy, but it's actually not so easy, because you have to figure out why 1 and 3 won't crash into each other and why 2 and 4 won't crash into each other. And the actual crash that happens is between 3 and 2. All right, okay. Here's a very interesting one, a very different kind of question. So this is a map, and you have 2 streets, street A and street B. The question says, north of street A there are 7 houses, east of street B there are 8 houses, south of street A there are 5 houses. How many houses are there west of street B? West of street B. Once again, an actual Math Kangaroo question. The correct answer is 4. And why is that? Like, please follow me. This is a fairly tricky question at first, but the actual logic involved here is fairly simple. It says north of street A, there are 7 houses. So this is street A. So north of street A, there are 7 houses, and south of street A, there are 5 houses. So south of street A, there are 5 houses. So north of street A 7, south of street A 5, which means in total there will be 7 plus 5 or 12 houses. So let's focus on this number 12. So we know now that the total number of houses is 12. And now let's look at the houses from the perspective of street B. So now we are told that east of street B, there are 8 houses. So there are 8 houses to the east of street B, and we also know that the total number of houses is 12. So west of street B, there must be 4 houses, because 4 plus 8, we want them to add up to 12, and 7 plus 5 is 12. So the total number of houses is 12, and therefore whatever is to the west of street B and to the east of street B, they must also add up to 12. So the correct answer is 4. Okay, here's your next one. In a queue in front of a ferry, there are 8 cars with 19 people in it. 8 cars with 19 people in total. There are either 2 or 3 people in each car. How many cars are there with exactly 2 people? How many cars with exactly 2 people? Let's calculate the answer step by step. So there are 8 cars with 19 people in it, and every car has either 2 or 3 people in it. So how do you calculate the number of cars with 2 people in it and the number of cars with 3 people in it? So we have 19 people in total. Now let's say there is just one car with 3 people. So let's say there is one car with 3 people, which would leave 16 people out of 19 to be accommodated in the cars with 2 people, and therefore we would need 8 cars with 2 people each. So 8 into 2, that's 16 people, and 1 car into 3, that's 3. So 3 plus 16 is 19. But then the number of cars would be 1 plus 8 or 9. But we are told that there are 8 cars only. So we need the number of cars to add up to 8. So if we had 2 cars instead of 1, then there would be, if we had 2 cars with 3 people each, then there would be 6 people in these 2 cars and 13 people left over. But we know that every car has either 2 or 3 people. So this possibility is not possible, because you can't have 13 people accommodated evenly in any number of cars. So let's go to then 3 cars with 3 people each. So if we had 3 cars with 3 people each, then you would have 9 people in these 3 cars, and then you would have 10 people left over, and those 10 people could be accommodated in 5 cars at 2 people per car. So 5 cars with 2 people each, so that would be 5 into 2 or 10, and then 3 cars with 3 people each. So 3 into 3 is 9, and 5 into 2 is 10. So 9 plus 10 is 19. And then what is the number of cars? So you have 3 cars with 3 people each, 5 cars with 2 people each. So 3 plus 5 is 8. And therefore this combination satisfies the constraints given to us. So there are exactly 5 cars with 2 people and 3 cars with 3 people. And therefore the answer for this problem is 5. 5 is the correct answer in this case. All right. This one is more straightforward. A building block is made up of 5 identical rectangles, as you see in this image. How many of the patterns shown on the right side can be made with 2 such building blocks without overlap? So you could combine this building block to make some of these figures. How many of these could you make? Okay, so here's how to do this systematically. You have to observe that in this building block, you have 5 units, 5 blocks, 5 rectangles arranged in this kind of an inverted U manner, like this. So you just have to now figure out if some of these could be made using this block. So you have this here and this here. So yes, you put 2 of these 2 together like this, you will get this. So this works. and then what about this one? So you have this here and this here. So this would also be, this can also be made using two of these blocks. Similarly, this here can also be made using these two of these blocks, and this one here can also be made. So this here and this here, and you can put two blocks together like that to get that bottom right figure. But what about this one? You can't make this one, because if you take this here, you are only left with these three rectangles here. So you can't make this one, but you can make the other four. So the answer is 4 in this case. You can make 4 of these patterns. All right. Okay. This question actually has kangaroos. It's a kangaroo math question, actually has kangaroos. 6 beavers and 2 kangaroos are standing on the field in this order, as you can see, 1 to 8. And of 3 animals in a row, there is always exactly 1 kangaroo. So if you take any 3 of these animals in a row like this, you should always have 1 kangaroo in 3 animals, among 3 animals in a row. So on which of these numbers stands a kangaroo? So which of these 2 numbers must have a kangaroo? So what you want is that if you take any 3 animals in a row, there must be 1 kangaroo among them. Now imagine what happens if you put a kangaroo here. If you put a kangaroo on number 1, then you just have 1 more kangaroo that you have to place somewhere among these other 7 positions, and then you will not be able to get a situation where every row of 3 numbers gives you a kangaroo. So for example, if you put 1 here, and let's say you put 1 kangaroo here, then this row of 3 animals won't have a kangaroo, this row of 3 animals won't have a kangaroo, and so on. So you can't put your kangaroo over here, and you can check that you can also not put your kangaroo over here, because if you put your kangaroo over here, again you have 6 positions here, and just 1 kangaroo is not enough to cover those 6 positions in a way where you get 3 kangaroos in every row of 3 positions. So this also won't work, and similarly this here and this here also won't work. And intuitively the way you can think about this is these positions are too close to the edge of the sequence, and therefore they don't give you enough coverage in the middle. And what you need is whatever sequence of 3 animals you take, you always must find a kangaroo in them. But if you place a kangaroo over here and if you place a kangaroo over here, this arrangement will work, because if you take every combination of 3 rows, three animals in a row, like if you take this, you get a kangaroo. If you take this, you get a kangaroo. If you take this, you get a kangaroo again. And if you take now 4, 5, 6, you get this kangaroo. 5, 6, 7, you get this kangaroo again. 6, 7, 8, you get this kangaroo again. So this arrangement where you have 1 kangaroo at number 3 and 1 at number 6 will satisfy this constraint given in the problem. So the answer is 3 and 6. All right. Okay, now this one is maybe slightly more challenging, so take your time to think through this one. An underground line with 6 stations A, B, C, D, E, F is shown here, and the train stops at every station, and after reaching the end of the line at A or F, the train continues in the opposite direction. So for example, if the train reaches here at stop A, then it will go to stop B and so on till F, then it will reverse its direction. The train starts the journey at station B here, and the first stop is at station C. So it's initially going in this direction. At which station will be the 46th stop? 46th stop. Okay. Now I will show you systematically how to solve this problem, so follow me carefully. What I am going to observe is that the train is starting from position B and it's going towards the right. So this is the first stop, the second stop, the third stop, and the fourth stop. So station F, the right end point, is the fourth stop for the first time. So it's the fourth stop, and then the train reverses its direction. So because this is fourth, then the train starts moving here. So then this is E is 5th, 6th, 7th, 8th, 9th. So station A is the 9th stop in the sequence. So I will put station A over here, and this is the 9th stop in the sequence. And then the train reverses direction again, so it starts going towards F again. So station A was 9th, then B would be 10th, C is 11th, 12th, 13th, 14th. So station F is then the 14th stop in the sequence, and then the train reverses direction again. So 15th, 16th, 17th, 18th, 19th. So station A is the 19th stop again, and now you can start to see the pattern. So 4, 9, 14, 19, 24, 29 and so on, which means that station F will also be the 44th stop in this sequence. So station F is the 44th stop, and the reason I am taking 44 is because I want to get to the 46th stop. So the nearest number in this pattern seems to be 44. So station F will be the 44th stop, and then E would be 45th and D would be 46th. So station D would be the 46th stop in the sequence. So this is how you could do it systematically by observing what station F is. For the first time, it's the 4th stop, and station A is the 9th stop, then 14th, 19th and so on and so forth. Okay, so this one was a bit more challenging, but once again you have to reason your way through such problems systematically, and there is no reason why you wouldn't be able to solve them. Alright, here is your next problem. 5 clocks on a wall, A, B, C, D, E. One clock is 1 hour ahead, another one is 1 hour late, and one is correct. And 2 clocks have stopped working. So which clock shows the correct time? Which clock shows the correct time? Now this one I find very interesting. Here's how you would solve this systematically. And once again, students, the idea is not to guess. And I can see a lot of you are, writing your answers very rapidly into the chat. Some of you might be guessing, some of you might have thought about it systematically. But the thing about competitive math is you can't guess your way to success. You have to solve every problem systematically with the right kind of reasoning. So what do we do here? Well, we are told that one clock is 1 hour ahead. 1 hour ahead means it's 1 hour faster, and one clock is 1 hour late. So if, for example, right now let's say is 12 p.m., then a clock that's 1 hour ahead would be saying 1 p.m. and a clock that's 1 hour late would be saying 11 a.m., 1 hour before this. So we are told that one clock is 1 hour ahead, one is 1 hour late, and one is correct. And that means that among these 5 clocks, we must have a set of 3 clocks which differ in their times by just 1 hour. Because we are told that one clock is on time, so let me represent this thing here as the clock on time, and then one clock is 1 hour ahead, so there is a gap of 1 hour, and then one clock is 1 hour behind, so there is another clock that should be at a gap of 1 hour. So you should have 3 clocks with times that have differences of 1 hour each, and you can see that those clocks are B, C and D, because B is at 2, D is at 3 and C is at 4. So 2, 3 and 4. So this sequence of 3 clocks will satisfy this first condition here, and then 2 clocks have stopped working. So now this immediately tells us that clock D should be the right clock, and then clock C is 1 hour ahead, clock B is 1 hour behind, and then A and E seem to have stopped working. So we can just say that these are the 2 clocks that have stopped working. So option D is the correct answer in this case. D is the answer. D is correct, C is 1 hour ahead, B is 1 hour behind. All right. Okay, now this one a bit more challenging, very interesting. A teacher writes exactly one number from 1 to 7 in each circle. So these are the circles you see, empty circles, and a teacher writes the numbers 1 to 7 among these circles. And when he adds up the 2 numbers of circles that are next to each other, he gets the number that is written between the 2 circles. So for example, if you had a 3 here, you would have a 5 here, because 3 plus 5 should add up to 8. But we are not really given the numbers in the circles. We are just told that those numbers are the numbers from 1 to 7, and we are just told that the sum of every pair of numbers is these numbers that you can see written here. What number should replace the question mark here? That's the question. What number should replace the question mark? I see some answers as 15. So just remember the numbers being added are the numbers in the circles to give these numbers between them. You're not adding these numbers. So you're not adding 9 and 6 to get 15. You are adding the numbers in these two circles to get 9 or in these two circles to get 6 and so on. And therefore you have to figure out what will come in this question mark here. Okay, once again, I'm going to show you how to solve this systematically. And the goal is not to guess our way to the answer. The goal is to find a systematic line of reasoning that tells us what the answer should be. So you need these two numbers. Let me label this circle as A and this one as B. So you need the numbers in A and B to add up to 9. And you are told that the numbers in the circles are from 1 to 7. So let's think about which two numbers from 1 to 7 could add up to 9. So you can't have 1 and 8 because there is no 8. You could have 2 and 7. You could have 3 and 6, or you could have 4 and 5. So let's try each of these combinations for these two circles. If you put a 2 and a 7 here like this, 2 here and 7 here, that won't work because this number 7 and this number here should add up to this number here, which is 6. But 6 is smaller than 7. So that doesn't work. But if I put a 7 here and a 2 here, then what happens? Then this 2 means that because I need a 6, sum of 6 here, this should have a 4 here, and then this should have a 5 here, and then this should have a 3 here because 3 and 5 is 8, and then this should have a 4 here, but 4 has already been used here. So this placement of 7 here and 2 here also does not work. So I can rule out 2 and 7. These circles don't contain 2 and 7. Now let's investigate the second combination, 3 and 6. So if I put a 3 here and a 6 here, does that work? Well, it again does not work because this number 6 plus whatever comes here should add up to 6. But that means this would be 0 and there is no 0 in the circles. So 3 and 6 doesn't work. But what if I make this a 6 and this a 3? Would that work? Well, once again it won't work because if you have a 3 here, you need a 3 here because 3 and 3 must sum to 6. And you can't, there's no digit, no number being repeated. So you can again say that 3 and 6 also don't work. And therefore now let's try 4 and 5 perhaps. So I put a 4 here and I put a 5 here. So 5 means, but okay, 4 here means there would be a 4 here, and that once again doesn't work because the 4 is being repeated. So now finally let me put a 5 here and a 4 here, and let me see if this works. So if there's a 4 here, there would be a 2 here because 4 plus 2 is 6, and then there would be a 7 here, great, 2 plus 7 is 9, and then 7 here means 1 here because 1 plus 7 is 8, and then 1 here means 6 here because 1 plus 6 is 7, and 6 here means 3 here, and 3 and 5 is 8. Wow, so every combination of two circles gives us the correct sum in the middle, and therefore the question mark here is 4, and we've also figured out the placement of the other digits. So the answer is 4 in this case. The question mark contains 4. All right, okay. Now here's, I think, the last couple of questions from Kangaroo Math, and then we'll go to the next section. So this one says, a terrace is covered with square tiles of different sizes. So you can see that there are square tiles of different sizes. The smallest tile has a perimeter of 80 centimeter. The smallest tile has a perimeter. What is perimeter? It is the boundary length around the figure. The smallest tile has a perimeter of 80 centimeter. A snake lay down along the edges of the tiles. So this black, dark black thing is the snake. How long is the snake? So the smallest tile has a perimeter of 80 centimeters. So look at this, these tiles here. These seem to be the smallest tiles, and we are told that these have a perimeter of 80 centimeters, which means the sum of the 4 sides is 80 centimeters, which means every side should be 20 centimeters because 20 times 4 is 80. So now we know that the edge length of the smallest tile is 20 centimeters. Now we can figure out the length of each segment of the snake. So this one here is 20, and so 20, this is 20, and now this edge is actually two 20s put together because this square is actually the double of this square. So this one will be 40, this one will be 40, and then this one is also 40, 40, 40, and then what about this big square here? So this big square you can see has this as the edge length, which is actually 20, 20, 20 or 60. So you'll get a 60 here, and then a 60 and 20, which is 80 over here, and then 20 over here, and then 20 over here. Okay, so I think I have counted all the segments now. So let's now just run the sum and see what we get. So 20 and 20, 40, and then I have 140, 2, 3, 4, 5, 6. So 40 into 6, 240, and 60, 300, 380, 400, and 420. So 420 is the sum in this case. So you had to just carefully count the length of every segment in this case, add them all up, and you get the answer as 420. All right, I see a lot of correct answers now. Yes. Here is the last question from Math Kangaroo, and then we'll go to the next contest for this class. Now this one says, okay, ignore the title here, the title is for the last slide, but the problem says 4 posts are placed along a 120-meter long running track. So you can see this track here is 120 meters long. How many more posts have to be placed so that the running track is split into equally long sections? So right now the sections are of uneven length. You have 24 here, you have 30 here, and you have 66 here. Now you want to insert some more posts or pillars or posts between them so that you get sections of equal spacing. So what is the minimum number of posts you must put in between these so that you get sections of the same length? So listen to this one carefully, because this one is based on an idea that might come across as a bit challenging, but here's what you need to do. So you need to observe that the distance or the gap here or the section length here is 24, but here it is 30. And 24 and 30, if you think about their factors, what is the largest factor that is common to both 24 and 30? That is actually 6, and 6 is also a factor of 66. So the factors of 24, 30 and 66, if you look at all of those, you will find that 6 is the largest factor that is common to 24 and 30 and 66. So if you insert posts at spacings or distances of 6 meters each, so you let's say insert 3 posts here at distances of 6 like this. So 6, 6, 6 and 6. So you have now split this section into smaller sections of equal length. So you have inserted 3 posts here. The same thing you can do here. You can insert 4 posts here like this to get sections of equal length. So 6, 6, 6, 6 and 6, 5 sixes, which is 30. Great. So you have inserted 4 posts here. So 3 here and 4 here. And then what about this one? How many posts will you need to insert here? You will need to insert, because this is 66, 66 by 6 is 11. So 11 means that you need 11 sections, which means you will need to insert 10 posts, 1 less than the number of sections. So the reason why 1 less than the number of sections, because let's say if you had this segment here AB, and I tell you to divide this segment into let's say 4 sections. So how many points do you need to place on this segment to divide it into 4 smaller segments? You would place 3 points. Let's call them C, D and E, because these 3 points would give you 4 segments, 1, 2, 3 and 4. So the same thing you can do over here. You can place 10 posts here. So let me just place them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that gives you 11 sections of length 6 each. So you have placed 10 here, and therefore what do you get? You get 3, 4 and 10, which is 17. So 17 posts is what you will need to place over here. So once again an actual Kangaroo Math question, a bit challenging, but this is aimed at students of your level, so you need to master the art of solving such problems. All right, okay. So a little bit about this contest Math Kangaroo. Some of you might have taken it already, some of you might be planning to. So it has these interesting problems, the kind that we did the kinds of problems we solved just now, but they're not too difficult. I hope you did not find them to be too difficult. If you think about every problem systematically, you will be able to solve the problems that come up on this context in this contest. You also get exciting awards for this exam, like $1,000 college grant, some other freebies and so on. And this contest is globally recognized. It's taken by kids from over 90 plus countries, and it happens for grades 1 to 12. And I think the next exam is going to happen in March of next year, and the registration deadline is December of this year. So if you're interested in taking this contest or this exam, you can actually register on mathkangaroo.org and go ahead and sign yourself up for this contest.